Okay, thanks a lot for this wonderful invitation. It is a pleasure and honor for me to be with you. And so in this talk, I will tell you about our recent efforts to look for dark matter emission in highly energetic cosmic ray data. So this is the outline of my talk. So in the first part, I will provide a very brief introduction to the topic of indirect dark matter detection. And then I will divide my talk in 3 different sections. So essentially, we are going to use different data sets, and we are going to make observations in different regions of the sky, and we are going to look for dark matter emission in different ranges of the dark matter mass spectrum. So in particular, between 10 and 10 to the 3 GeVs, 10 to the 3 and 10 to the 5 GeVs, and lastly, super heavy dark matter between 10 to the 4 and 10 to the 16 GeVs. All right, without further ado, let's start. So there is overwhelming evidence for the existence of dark matter, which comes mainly from gravitational observations of dark matter at different scales, so from galactic scales to cosmological scales. And all these observations are consistent with a picture in which dark matter makes up for about 85% of the mass content of the universe. Now, one of the most important questions in modern science corresponds to what's the nature of dark matter, meaning we want to know what is the mass of the dark matter particles, and we also want to know what is the scale of the interaction of these dark matter particles. So one of the most promising ways to try solve this puzzle is indirect dark matter detection. So in indirect dark matter detection, there are models that extend the standard model of particle physics, so physics beyond the standard model, that predict that dark matter can self-annihilate or decay in regions of the sky where dark matter is very dense. And so we can use some surveys that scan the sky in the full electromagnetic spectrum. There are also experimental observatories, telescopes that also observed different cosmic ray species, and we can definitely look and prove our favorite dark matter model. So as I mentioned, dark matter can self-annihilate, and then produce standard model particles, so ordinary particles, cosmic ray, so charged cosmic rays, neutral cosmic rays, which we can observe with these telescopes. So this is the prediction. So this is the flux predicted from dark matter self-annihilation. So the flux depends on the annihilation rate, also the photon energy or the cosmic ray energy distribution, or the cosmic ray spectra, essentially, and also depends on the line of sight integration of the square of the dark matter density. So let's focus for a moment on the energy distribution of the cosmic ray species. And so this is how it looks like. So from dark matter self-annihilation, you produce neutral or charged pions, which rapidly decay and create showers of charged cosmic rays and neutral cosmic rays. And this is how it, so this is the energy distribution of these cosmic ray particles. Now, I should note here that this spectra expected from dark matter annihilation is very similar actually to the usual astrophysical processes, such as the emission from supernovae or pulsars and so forth. And so that's going to be a challenge in indirect dark matter detection. Now, regarding this factor here, so the so-called J factor, or this line of sight integration, so this is how we do. So essentially what we do is we use embodied simulations of dark matter, which predict the distribution of the dark matter density, and then we can perform this line of sight integration. Now, from this exercise, we get that the highest intensity of dark matter is expected to be in the center of the galaxy. Now, there are some other places in the sky, such as dwarf spheroidal galaxies, galaxy clusters, where there is also expected some dark matter emission. We will also expect some dark matter emission, and but definitely the most important place to look for dark matter, so the highest intensity, is expected to come from the center of the galaxy. But unfortunately, this is also a place where there are largest uncertainties, and essentially, we need to deal with this in some way. But the Galactic Center is definitely the best place to look for dark matter, in the sense that the highest intensity is expected from this region. Now, this is sort of a summary of the current status in the indirect dark matter detection community. So basically, there are a lot of potential dark matter detections. So all of these are published in prestigious journals, and there are potential dark matter signals in different cosmic ray species, for instance, in X-rays, gamma rays, antiproton, soft gamma rays. So there are, and this is not a complete summary actually of all the potential non-gravitational detectors of dark matter. Now, one general characteristic of all these potential signatures of dark matter is that they all assume a simplistic background. And so at the moment, it's not clear where these potential detections are actually real, or they are just due to imperfections of the astrophysical background, or just some sort of statistical fluctuations. And in fact, two of these potential detections have been shown to be not due to dark matter. So this is the so-called 130 GeV line, which we now understand that it is actually due to just instrumental systematics of the Fermi detector, and also the so-called WMAP haze or Planck haze, which we know is real, but so there is consensus that the signal is potentially due to so it's definitely due to, astrophysical processes, so secular astrophysical processes possibly related to the Galactic Center. So yes, so basically, so this is the summary in our field in indirect thermal detection. So essentially, the propagation of cosmic ray particles, so the microphysics of this process is very well understood, but the exact form of the magnetic fields, the interstellar radiation fields are not very well known. Also, there are a lot of uncertainties in the gas content in our galaxy, and so basically making the tail predictions for these for the expected signals from dark matter annihilation is quite uncertain, just because all these astrophysical components are very uncertain. So I put a lot of effort in my research to try improve our astrophysical background models to basically get higher sensitivity for dark matter searches with this indirect dark matter detection technique. All right, so now I will start describing our efforts to look for dark matter in this mass range. So these are self-annihilating dark matter in the mass range between 10 GeV and 10 to the 3 GeV. And so, as I already mentioned, the center of the galaxy is a very special place to look for dark matter, and I will focus on the center of the galaxy using data from the Fermi telescope. All right, so as you might know, observations of the center of the galaxy with the Fermi telescope have revealed an excess emission, which is called the Galactic Center excess. So this Galactic Center excess was actually claimed in 2009 by Hooper and Wino. And since then, many research teams have reanalyzed this excess emission and confirmed the existence of this excess. And I should also point out that the Fermi-Lat collaboration has basically confirmed the existence of this excess. And so it has been very interesting because of the fact that this galactic center excess can be explained with sort of almost a vanilla-like dark matter model. And so this has motivated a lot of work, especially particle physicists. They have been a lot, so there has been a lot of excitement in the dark matter community. And so, but as you see, so this access has been for a while there, and people have learned a lot from this access emission. And this is a summary of this galactic center excess. So essentially, there are three different pieces of information that we can get from the signal. So one is the photon energy distribution. Second is the spatial morphology of the signal. And third is the photon count statistics. So regarding the first, so the energy distribution or the spectra of the signal, we understand that these spectra, so this is a peaked spectra, which can be explained by the overall emission from an unresolved population of millisecond pulsars in the center of the galaxy. So I'm going to provide a bit more details about that in the next slide. But so this can be explained by new millisecond pulsars in the center of the galaxy. So in fact, we need about 40,000 new millisecond pulsars in the center of the galaxy to explain this access. Now, if you look at the spatial morphology, even though at the beginning, people thought that the spatial morphology of the signal was consistent with that of dark matter, recent analysis, including my own and some other independent teams, have shown that the spatial morphology of the signal is actually correlated with the stellar mass in the galactic center. So this observation strongly supports the millisecond pulsar hypothesis, because millisecond pulsars basically live with the stars, and so are stars. And so we expect these millisecond pulsars to be distributed as these stellar maps that we can get for the center of the galaxy. Now, you can also look the photon so investigate the photon count statistics. And so essentially, if this galactic center excess were due to dark matter self-annihilation, you should expect that the photon count statistics was purely Poissonian statistics, or was explained by Poissonian statistics. Now, if instead of dark matter, this galactic center excess is due to millisecond pulsars, then you should expect deviations from these Poissonian statistics. So you should expect some clustering of photons in the center of the galaxy, and you can use this observation in principle to distinguish between the dark matter explanation and the millisecond pulsar explanation. So people have used different techniques, have used this non-Poissonian template fit, have used this wavelet method to look for peaks in the photon flux in the center of the galaxy. And at the moment, there is no consensus, at least in this, with this characteristic of the signal. So please stay tuned. So there are a lot of people thinking about this, but these two observations of both the spectra and the spatial morphology allow us to discriminate the millisecond pulsar hypothesis from the dark matter hypothesis. And so the current data strongly supports the millisecond pulsar explanation for this galactic center excess. So here I show, so this is a gamma ray observation from a globular cluster, so the 47 Tucane. So globular clusters are very old stellar systems which have a lot of millisecond pulsars in them. So if we observe these globular clusters in gamma rays, we can basically get the overall emission, gamma ray emission from tens of millisecond pulsars. And so here, this is what one of my collaborators, Kepa Asajian, realized very early after the first claim of this galactic center excess. So what he did was he basically showed here the galactic center spectra, which is shown here in these black points, and then he overplotted the spectra measured from different globular clusters in gamma rays. And so you see that the spectra is very similar. So the spectra that we get from the center of the galaxy is very similar to the spectra that we measure in globular clusters. This basically motivates this millisecond pulsar explanation for the galactic center excess. So we have also run some detailed population synthesis analysis, and we have shown that we need 40,000 millisecond pulsars to explain this galactic center excess. So just remember, millisecond pulsars are rapidly rotating neutron stars, which can produce gamma rays from the pulsar magnetosphere. And so far, basically, so I should stress this enough that this galactic center excess, even though we cannot definitely say for sure that the galactic center excess is due to millisecond pulsars, so current data supports these hypotheses. So there is a strong support for this millisecond pulsar hypothesis. And so what we need to definitely put the last nail in the coffin for this galactic center excess is definitely to detect these individual pulsars. And there are surveys going on in radio and in X-ray. So there are people thinking about scanning in X-rays and radio to look for these objects. And that's basically what we need to completely close this potential dark matter detection. So now let me move on to show you what we did new in this new paper, which we published recently in August this year with some of my American collaborators. So this is what we did essentially. So we reanalyzed data from the center of the galaxy with the Fermi telescope. So we analyzed 8 years of Fermi data, and we here show our astrophysical background model for this region of the sky. So essentially, electrons accelerated by cosmic ray sources produce, so these electrons upscatter ambient photons to high energies, and they produce inverse Compton. And so we predict this inverse Compton by solving the cosmic ray transport equation using some publicly available codes to do this. So in particular, we use a code called GalProp, so the latest version of this code to produce these maps. And we divide the maps in different galactocentric rings. And so this allows us to better account for potential systematics in these maps. Also, cosmic ray protons interacting with interstellar gas in this region produce hadronic gamma rays. And so we use a model-independent way to model this hadronic emission by producing different maps of atomic hydrogen and molecular hydrogen. And so in our analysis, we run some hydrodynamical simulations with interstellar gas, which allows us to better track the distribution of gas in the center of the galaxy. Also, this map here shows the compact objects. So these are pulsars, supernova remnants, and some other compact objects which emit gamma rays and which we cannot detect or we cannot resolve with the Fermi telescope. And so these are called gamma ray point sources. And we use the latest catalog created by the Fermi collaboration. Now, this is the Fermi balls. And so the Fermi balls are these giant non-thermal structures which we observe towards the center of the galaxy, and we use some image reconstruction techniques to get a better model for these important components at the center of the galaxy. And now here we also include these galactic balls. So this is the distribution of stars. We use some new data analysis techniques to so basically what we do is we use red clump giants, for which we can learn the distance quite well. And so we create maps for the galactic bulge using these red clump giants. And so basically we use a maximum likelihood technique, and we feed all these components to the center of the galaxy, gamma rays from the center of the galaxy, and these are our results. So this is the data, gamma ray data from the inner 40 by 40 degrees of the center of the galaxy, and we divide the data in different energy ranges, energy beams, so between 1 and about 3 GeVs, 3 and about 12, 12 and about 160 GeVs. This is the data, and this is the best fit model to this data. And so you see here that we have a reasonably good model for the region of the sky. So our best fit model is almost, at least by eye, almost impossible to distinguish from the data. And one thing that we can do is basically to subtract this model from the data and look at the residuals. So if there were, dark matter annihilation in the center of the galaxy, what you should expect to see in these residuals is something that looks roughly spherically symmetric or ellipsoidal, but we in fact are not detecting anything like that. So we are finding some non-structured, almost Gaussian residuals. And but I should mention that our model does not fit the data perfectly well. So this is not a formal good fit to the center of the galaxy. So in fact, the residuals shows that we fit the data at a 30% level. So there is still work to be done, and I'm trying to basically improve our astrophysical background model and hopefully improve the goodness of the fit. But currently, this is the best astrophysical background model for the center of the galaxy, and our current knowledge basically indicates that there is no room for dark matter annihilation in the center of the galaxy. So we can use basically this fact to impose robust constraints on the dark matter properties using this null observation of dark matter in the center of the galaxy. So in our analysis, we account for the systematic uncertainties in the dark matter distribution in the center of the galaxy. So it's interesting that some recent simulations of dark matter that include baryonic effects, they all predict, so all simulations predicted Caspi dark matter profiles, and that the spatial morphology of dark matter was completely spherically symmetric. But now, so these new simulations that account for baryonic effects predict these dark matter profiles that are actually spheroidal or ellipsoidal, and they also predict a core to so they develop a core in the center of the galaxy. So in our analysis, we account for all these uncertainties so we are agnostic as to what's the actual spatial morphology of dark matter in the center of the galaxy, and we account for all these uncertainties using a Bayesian technique. So these are our results. Basically, this is the dark matter annihilation rate, and this is the dark matter mass. So we divide our limits into the different spatial morphologies. So here for NFW profiles, or Navarro frame wide profiles, and here for the core profiles. So this green line here shows the 95% confidence limits that you get by null observations in dwarf spheroidal galaxies. So all this parameter space here is ruled out by null observations of dark matter in dwarf spheroidal galaxies. Now we show here that for different assumptions of the dark matter distribution, or different assumptions of the astrophysical background, the gamma ray astrophysical background, you get some variations in the limits. Also here, and basically conservatively, we suggest people to use our weakest limits, so the weakest limits that we get from our analysis. So these are basically the full results from our analysis. Essentially, the results are that from null observations of dark matter in the center of the galaxy, we can get constraints that are a factor of a few stronger than the ones that we get from the dwarf spheroidal galaxies. So overall, we are able to rule out dark matter particles with masses, so thermal dark matter particles with masses less than 400 GeVs. So these are our results for the null observations of dark matter in Fermi-Lat data. Now we are also interested in, so obviously we don't know what's the mass of the dark matter, and so we are also interested in very heavy dark matter. So they're also very well motivated by physics, by new theories of particle physics. And here we are going to also look for dark matter using look for dark matter in the center of the galaxy. So here we are going to use the forthcoming Cherenkov Telescope Array. So our results are published in this paper. So this paper was actually accepted something like 2 or 3 days ago, and it will be updated in arXiv very soon. So please check out the details if you're interested. So this is what we do. So obviously the Cherenkov Telescope Array has not been built yet. So it's going to start observations in 2022. I realized there is a big group of CTA in ICCUB, and so I don't probably need to provide a lot of details about it, but let me just briefly mention that CTA will observe gamma rays in the energy range between 10 GeVs and 100 TeVs. It's going to have an exquisite angular resolution of between 0.2 degrees and 0.02 degrees, and the place of the observation site that is going to have the best resolution or the best sensitivity, to the center of the galaxy is the southern side. So the side that is going to be built in Chile. Now, so as we know, the Cherenkov, so the CTA is a pointing is a pointing instrument, but CTA anyway can make diffuse observations of the center of the galaxy with a very clever and ambitious technique that the CTA people are going to use. So essentially what the CTA people are going to do in the center of the galaxy is combine, so these are the pointings of the instrument, and they are going to then combine all these observations to get the diffuse measurements in a very large region of the center of the galaxy. So this is going to be great. So the CTA plans to dedicate about 500 hours of observation time to the center of the galaxy, and we can use these observations to look for potential dark matter signals in this region of the sky. So here, as a case example, we use 2 very well-motivated models, dark matter models. So in particular, we're going to use the Wino and the Higgsino dark matter. Now, recent understanding of the spectra predicted by the Wino dark matter. So this is an archetype heavy dark matter candidate, and so we know that there are contributions to the annihilation rate and the photon spectra that is predicted by different processes. So these are corrections in perturbation theory that add new photons or due to, for instance, the Sommerfeld enhancement or the these continuous gamma rays, and there are these new contributions due to these contributions in perturbation theory. And so we basically here account for all these contributions in our analysis. So in a sense, this is a very realistic spectra that we are using. Now for the Higgsino case, we don't yet have the full technology to include all these contributions in perturbation theory, but in any case, we include the Higgsino case as a representative example. So these are basically the specifications of the model that we include. Now, as the CTA has not observed gamma rays yet from this region of the sky, then we need to make some predictions about what CTA is going to observe. And so our approach is basically highlighted here. So these are observations of diffuse gamma rays taking a lower energy. So these are taken with the Fermi telescope. And so one of the approaches that we take is that, so we make observations of the hadronic gamma rays, inverse quantum gamma rays, and then we feed that to Fermi data, and then we make extrapolations at this energy range. And so we can make some predictions for what CTA might be able to observe. So we have 2 different approaches for that. So one is that this extrapolation, and the other is that we can also solve the cosmic ray transport equation in this region of the sky and make predictions for how the gamma ray sky should look like in this energy range. And so this is our approach. Then what we do is we basically convolve these predictions with the instrument response function by the CTA and make these predictions for the count rate that is going to be observed by CTA. Now, one important thing to note here is that CTA, so the most important source is going to be the irreducible cosmic ray background. So these are cosmic rays that hit the atmosphere and produce gamma rays that cannot be easily distinguished from astrophysical gamma rays. So these are this is a very important component and a very important source of uncertainty. However, one important thing to notice is that the spatial morphology of this component is expected to be isotropic. And so we can use the very particular spatial morphology that is predicted for dark matter and other astrophysical components to distinguish the irreducible cosmic ray background from the expected astrophysical gamma rays and also the gamma rays expected from the new physics, so dark matter, for instance. And that's the approach that we take. And so so these are the results for our sensitivity analysis. So essentially, so these are the 2 sigma upper limits on the annihilation rate that CTA will be able to observe. So what you see here, so this is the annihilation rate that is predicted for the Wino dark matter case. Now, the thermal Wino is highlighted here, and this is the annihilation rate that for this thermal Wino that will explain the 100% of the dark matter density that we observed today. So we call this the thermal Wino. And you see here that CTA is going to have very good sensitivity to prove this dark matter model. So there are 2 orders of magnitude different between the prediction and the sensitivity of the instrument. And I should also note that, so essentially we are showing here that CTA is essentially currently the only experiment that is, or let me say this better. So it's the experiment that has the best sensitivity to these dark matter models so even including collider experiments and so on. So currently, we are showing that CTA has the best sensitivity to that and is going to actually have better sensitivity than the Hess telescope. Now, of course, the center of the galaxy, so the distribution of dark matter is very uncertain. And here we show the systematic uncertainties that are due to different choices of the, for instance, the core radius of the dark matter. So you see here that if we are very pessimistic and think that the dark matter profile can have a very large core radius, then you see that the uncertainties are going to be potentially 2 orders of magnitude. But this is ultra conservative, I will say, and in any case, the thermal Wino, even being very pessimistic, is going to, so CTA will be able to prove thermal Wino even in this very pessimistic case of a very large core, very large size for the core of the dark matter. Now, we also show here the Higgsino case. It's also very promising, but so at the moment, this is just a representative example, as we are not including some contributions that we know should be there. So I will leave it there and then move on to the last part of my talk, in which we basically look for super heavy dark matter. Now, super heavy dark matter, we know cannot be resolved with sorry, I was going to mention that the super heavy dark matter cannot self-annihilate, because essentially it would violate unitarity. And so instead we are left only with decaying dark matter. So for super heavy dark matter, they actually only produce these potential signals by decays. All right. And so these results are shown in this paper, and these are my collaborators for these results. So the first question that we must ask to look for the super heavy dark matter is, what is the expected energy distribution of, or what is expected spectra at source? Now, for this very heavy dark matter, it's actually very difficult to predict the spectra, just because the way we compute this spectra is by using some Monte Carlo simulation tools. Now, these Monte Carlo simulation tools or these Monte Carlo simulations become really computationally expensive when the dark matter is very massive. And so we couldn't use the usual tools. So for instance, Pythians and other Monte Carlo tools to run this. And so we were required to solve this by ourselves. And so essentially what we do is basically we solve the so-called DigiLab equations. So these are equations that account for the quantum chromodynamics contributions in these hadronic showers and these electromagnetic showers of these dark matter processes. And then what we do is we take the yields from these processes and feed that to Pythia, to this Monte Carlo tool, and then we follow the subsequent showers of these particles with these Monte Carlo tools. And so we basically were able to demonstrate that our technique matched the predictions by the Monte Carlo tools at lower energies, and then we make our predictions for these super heavy dark matter candidates. Now, one caveat of our approach is that we did not account for electroweak corrections, which we know are important at this very large mass scale. However, this is something that some people in the community have now solved. So I want to advertise here that there are some people in the community, in particular Bauer et al., which have basically used a very similar approach, so solving the DigiLab equation, then matching to Monte Carlo tools, and then, but they actually are now accounting for the electroweak corrections. So they are actually making their code publicly available, and so you can essentially use their code and predict these dark matter spectra for super heavy dark matter candidates, so which is very nice. All right, so this is what we do. So we are interested in this analysis to use all the potential cosmic ray species that we can use. So we are interested in using protons, electrons, neutrinos, gamma rays at the super heavy, at these super large energy scales. Now, we are also interested in particles that can come from the extragalactic region and also galactic region. And so we want to so in this analysis, we do a self-consistent analysis of the propagation of these particles from the extragalactic region and the galactic region. And so the message that we wanted, so one of the messages that we wanted to give to the community is to show what is the place in the sky which is best to look for this dark matter, where it is from the extragalactic region or the galactic region, and what is the cosmic ray species that provides also the best constraints or the best possibilities to detect dark matter. So this is what we do. So we predict the spectral source with this hybrid approach of using these Monte Carlo tools and solving the DigiLab equations essentially by hand. And then we propagate these particles using cosmic ray propagation tools. And so we take these tools that are actually built by cosmic ray astrophysicists, and we essentially do some customizations in order for us to propagate these these dark matter yields, essentially. So we customize some publicly available code. So cosmic ray propa for the propagation of these particles in the extragalactic region, and we also customize galprop for the solution of the cosmic ray transport equation in the galaxy, and the so-called Helmholtz. So this is also a code that solves the cosmic ray transport equation in the solar system. And so we use these three different codes in a self-consistent manner, propagate these particles until our detectors at Earth. And then what we do is we can then compare these predictions for the cosmic ray species with the very energetic detections or null detections, or I mean upper limits by these cosmic ray detectors. So here you see, for instance, so this is a particular case that I'm showing here for a dark matter mass of 10 to 12 GeVs. And since this is not self-annihilating dark matter, we are talking about actually decaying dark matter. So we assume a very large lifetime of 10 to 27 seconds. This is just an example of the spectra that we will get. And so this is the total spectra that you get. So including the galactic contributions and the extragalactic contributions. And this is the extragalactic one. And so, so you see here, this is for gamma rays, this is for antiprotons or protons, and this is for neutrinos. And so you see here that this data allows us to impose some constraints on the predicted on these dark matter models. So we can use these cosmic ray observatories essentially to impose some constraints on dark matter. So this is a summary of all the cosmic ray detectors and the cosmic ray data that we use. So in gamma rays, we use all this data. So we use, and this is the energy range that we use. So we use Fermi-Lat, we use Casamia, Cascade, Cascade Grande. This is the Pierre-Auger Observatory, and this is the telescope array. And we show here which observatory has actually detected signals in these energy ranges. And so actually these observatories have not detected signals, but anyway, they have put some constraints on the flux of these cosmic ray particles. And we can use these upper limits to impose constraints on that matter, essentially. So here, so you see here that these observatories have actually observed protons or antiprotons and positrons. And ICCUB has, as we know, observed astrophysical neutrinos, and we can use that to constrain our dark matter models. So basically, our statistical approach here is conservative. So essentially, what we assume here is that dark matter decays cannot overshoot either the measurements or the flux upper limits by all these detectors. And this is the way we essentially constrain in a sort of conservative manner these decaying dark matter models. And these are our results. So essentially what we so what we see here, so this is the lifetime of the dark matter particle. So this is the mass of the dark matter. And these here are actually lower limits. So the parameter space below these lines are ruled out by the null observations of dark matter by these cosmic ray detectors. So you see here that definitely, if you compare the cosmic rays that come from the extragalactic region as compared from the galactic region, you see that galactic cosmic rays allows to impose stronger constraints than the extragalactic region. And so in this self-consistent analysis, we show that this is the best way, or this is the best target region to look for decays in dark matter or to constrain dark matter. Now, you also see here that the strongest constraints in this mass range for masses lower than 10 to 8 GeVs come from Fermi-Lat, null observations in Fermi-Lat. Now, in this range between 10 to 8 and 10 to 11, come from null observations by Casamia, Cascade, Cascade Grande. So these are gamma ray observatories. Now, for between 10 to 9 or 10 to 10 GeVs to 10 to 16 GeVs, the strongest constraints come from null observations by the Pierre-Auger Observatory. So these are proton measurements by the Pierre-Auger Observatory. So, so these are basically the results. And so let me just move on to the conclusions part. So basically, in the first part of my talk, I have shown that, or we have shown, sorry, that the null observations of dark matter self-annihilation in the center of the galaxy rules out thermal dark matter with masses less than 400 GeVs. We have also shown that CTA is going to have significant sensitivity to Wino dark matter and potentially also Higgsino dark matter. And so I should stress that CTA is actually going to have significantly higher sensitivity that even collider experiments, which is something quite remarkable, I think, so that we are making progress in the particle physics using actually telescopes. I think that's extremely remarkable. Also, we can use these ultra high energy cosmic ray observations to even impose constraints or explore the parameter space for dark matter, for super heavy dark matter. And so this is the end of my talk. And so I'm happy to take questions that you might have. Thanks a lot for your attention.